Okay, so now for chapter 1.4, this is on quadratic equations. We'll be taking a look at equations that are of the form ax squared plus bx plus c is equal to 0. There's actually a lot to discuss when it comes to this. But let me just say for right now that this kind of expression is known as a quadratic expression. So I'll just write that for short. And quadratic just means that the highest power of x in this polynomial is 2. So the highest power is x squared, basically. And the first thing I want to discuss is something that is called the zero factor property. And I'll actually abbreviate this by ZFP for short. And the zero factor property, or ZFP, says the following. It says that if two things multiply to 0, then it must be true that either one of them was 0. So if A times B is 0, then either A is 0 or B is 0. Okay? Simple enough, and I think it makes sense because, well, 0 times anything is 0, so think of two non-zero numbers whose product is 0. The only way of making a product 0 is if one of them was 0 because of that property of 0, with multiplication. So let's see a quick example. Pretty basic example, I'd say. We have this product, x plus 1 times x minus 3 is equal to 0. Well, this implies from the ZFP that either x plus 1 is equal to 0 or x minus 3 is equal to 0. So what we can do now is we can solve each of these linear equations, a pretty simple linear equation, I'd say. Hope you agree. Subtract 1 to both sides in this case to get negative 1. And then here, add 3 to the other side to get x is equal to positive 3. So now altogether we can say that these are our two solutions. X is either going to be negative 1 or positive 3. So we can write that as a comma-separated list. X is equal to negative 1, comma 3. Just like that. And now we'll move on to next example. So this example is a little different in the sense that it's not already factored for us, but if we can factor this, then we can apply the zero factor property directly. So let's see that. If you don't remember how to factor, just at least know this. If you have x squared and there's no number in front of x squared, all we're really doing is looking for two numbers whose product is the constant and whose sum is the linear coefficient. So we're looking for two numbers that multiply to this and add to this. Generally, people make an X like this to organize your thoughts. So we're looking for two numbers that multiply to positive 4 and add to negative 5. Now the only two numbers I know that multiply to 4 are either 2 and 2 or 4 and 1. Okay? 2 times 2 is 4, 4 times 1 is 4. Now notice if it's 4 and 1, 4 and 1 do multiply to positive 4, but they add to positive 5, not negative 5. If they were both negative, however, they would indeed add to negative 5, and look at that. They still multiply to positive 4 because a negative times negative is positive. Great. So what this means now is that we can factor this as x plus each of these numbers we got from this method. The two numbers that multiplied to the last one and added to the middle one will be what we're going to add to x in each of the factors. Namely, x minus 4 times x minus 1 is how you would factor the non-zero side in this case. And you can check that when you FOIL this out, you indeed get the original polynomial on the left, and it does work actually. Now we can apply the zero factor property, and either this is 0, and if you kind of think how we did this, if you add 4 to the other side, imagine x minus 4 equals 0. I can write it real quick over here. If x minus 4 is equal to 0, imagine adding 4 to the other side, and you get x is equal to positive 4. The reason why I say imagine is because we're going to be doing this a lot really quickly. We're not going to get this distract us, I guess. So imagine adding 4 to the other side, you get x is equal to positive 4. Imagine adding 1 to the other side when x minus 1 is equal to 0. You get x is equal to positive 1. This makes the process a little more seamless. And basically what I'm trying to convey is that anytime you have x minus a number or even x plus a number as your factors, x will just be equal to the opposite of that number because of the way this works. X minus 4 equals 0, x is equal to positive 4. X plus 1 is equal to 0, x is equal to negative 1. It'll always work like that because that's how you solve this type of linear equation. If x plus a is equal to 0, then x will equal the opposite of a, even if a was negative. Okay, so now for this next example, well, we're going to try to get it in that formula like where 0 is on one side and everything else is on the other side, and it's a quadratic expression. So first, of course, we're going to simplify by getting rid of parentheses, so I'm going to distribute in this case. And then we're going to move things by adding or subtracting. So let's see, we get 2x times x is 2x times x, which is 2x squared. Negative 1 times 2x is negative 2x. Everything else stays the same. And now I'm going to move all this to this side so the 0's on the right. So I'm going to subtract 3 and add x. Notice x combines with this negative 2x part. Negative 3 I'm going to sneak in right in between the x term and the equality symbol. So these cancel on the right. So on the right we're left with 0 just like we want. On the left we have 2x squared. Negative 2x plus x is negative 1x, or just negative x. And then we have the negative 3 that we snuck in between. Okay, great. Now here, this does not satisfy the trick I showed you earlier to factor, because that I said would only be when there's no number in front of x squared. Sometimes, if you're lucky, they all have that number in common, so you can factor it out. So if, for instance, it was 2x squared minus 4x plus 6, they all have 2 in common, so you can actually divide 2 out, or factor 2 out from the expression, and then factor this. So in this case, just to kind of show you, this factors as, well, I guess this one doesn't actually factor, but that's beside the point. You know what? Let me just make this negative so it does factor. And I'll talk more in a little bit about what happens when it doesn't factor and when it does factor. But for right now, we're going to focus on ones that factor only. And this factors as x minus 3 times x plus 1. And that, of course, is because 3 and 1 are the two numbers that multiply to 3. And if it's negative 3 and positive 1, they multiply to negative 3. If you add negative 3 and positive 1, they add to negative 2. So that works. The 2 is still on the outside. Okay, but that was just a quick example of what happens when they all have that number in common. You can pull it out. Then you can continue with that procedure I just showed. However, in the case we're in right now, they don't all have that in common, so can it be factored? In this case, it actually can be factored. And remember, when we're factoring, really what we're doing is we are reverse engineering the process of foiling. So what I'm doing here is I'm looking for two numbers that multiply to 2x squared. Notice 2 times 1 is 2, so I have no choice. I know it's going to be 2x and x. Those multiply to 2x squared. And let me just show you in red what we're attempting to reverse engineer, the foiling process. So if you don't remember, foiling process is the first, outer, inner, and then last two terms all multiply together. Now, the first two multiply to 2x squared. That's great. Now, what two numbers multiply to negative 3? So notice I'm writing minuses. I always write minuses as just default. I'll change those signs possibly, but right now I'm just writing it minuses just so I have something there. Okay? You don't have to write anything though if you don't want to until the very end. That's fine. So either it's going to be 1 and 3 like this, or possibly 3 and 1 like this. In the previous example we saw when we were factoring, the order didn't matter because they were both x. Here, since it's 2x and x, it would be different if we had 1 and 3 in different orders. One case we'd have 2x minus 1 and then x minus 3. In the other case we'd have 2x minus 3 and x minus 1. It wouldn't be the same factorization. So notice, no matter which order they're in, 3 times 1 and 1 times 3 still multiply to 3. But we can check each of these to see which ones actually work. So let's try 1 and 3. Now again, the signs I don't know. So let's see. 2x times x is 2x squared. 2x times 3 is going to be 6x. The sign I'm not sure yet. So let's just write minus for now. And then what? Oh, then a negative 1x. Negative 1 times x is negative x. And then 1 times 3 will be 3. I want it to be negative 3. So the question is there a way that we can change these signs so that the resulting term after combining like terms with these two terms ends up being negative x? And the answer is no. Because if they're both negative, it's negative 7x. If they're both positive, it's positive 7x. And if one's negative and the other one's positive, it's either positive 5x or negative 5x, and you can try those out if you want. So long story short, this is the wrong combination. 1 and 3 is the wrong combination. So now we'll try 3 and 1, and we'll see if this works. Now remember, the outer two terms, so the first terms and the last terms basically, will still be 2x squared and negative 3. That's fine. What we're concerned about are the outer and inner multiplied. So the outer multiplied in this case will be negative 2x, and then the inner multiplied will be negative 3x. Now back to that question I asked, is there any way we can change these signs for the result to combine to negative x? And the answer is yes. If we were to make this positive 2x and leave that as negative 3x, then they do combine to negative x. And if you look back at this, how do we get positive 2x? It would have to be 2x times positive 1, so that would change to positive, and see how I change the sign. And negative 3x would still leave this negative. And then finally, look at this. Negative 3 times positive 1 is indeed negative 3, so the signs actually check out. So we've actually checked this by foiling, which is interesting. With the other method I showed you earlier, I didn't actually check it for you. I said you could check it and it would work if you foiled it out. In this case, we had to check it to see what it is, so it's a little different. This method, by the way, is called a guess and check method. There are other methods out there. I'm going to do another example in a bit where we'll do something different, but let's continue with this. We're not done. We factored only. Next step finally is to use the zero factor property. So either 2x minus 3 is equal to 0, or x plus 1 is equal to 0. Now x plus 1 equals 0, we've seen that already. We know the answer is going to be x equals negative 1. Why? Because you just change the sign. Notice, subtracting 1 to the other side gives you x is equal to negative 1. Here, we'd have to add 3 to both sides, and then finally divide both sides by 2. So we get 3 over 2. So altogether, each of these combines to the comma separated list, x is equal to 3 over 2, comma negative 1. And it doesn't matter which order you write your comma separated list in, by the way. So I spoke about these types of factors. X is just going to be equal to the opposite number, so change the sign. Here, you do change the sign. Notice negative 3, the answer was positive 3, but it's over 2. So that's clearly the case that you divide by the number in front. So if you want to go from here to your answer right away, you can. Change the signs and then divide by any number in front of x. If there is no number in front of x, you don't have any division to do. Okay, so now let's see one a little more complicated. Okay, so like I was saying, this one's a little more complicated. What I'm going to do here is I'm going to show you something called the AC method. What it allows us to do is multiply the outer two. I mean, if you think of how this is set up, it's ax squared plus bx plus c. So the reason why it's called the AC method is you're multiplying a and c together. So multiplying these numbers, we get 36. Okay, so now getting back to that x method of organizing your thoughts I showed you earlier, I said you can't do it when there's a number in front of x squared like there is here, but if you use the AC method to multiply a and c together, you actually can use this method, but there are little quirks. A little bit of quirks. And the first is that you multiply to the product, not to the last number. Okay? You still add to the middle number, positive 12 in this case. And the two numbers that work, you're going to write here just like usual, but we'll write them a little lower, and we'll see why in a second. In this case, what two numbers multiply to 36 and add to 12? Well, if you actually write out all possible combinations, 36 is 1 times 36, 2 times 18, 3 times 12, 4 times 9, and 6 times 6. And if you add these numbers up, 6 times 6 are the factors of 36 that actually add to 12. So this is kind of a way you can create all of these numbers or generate all of the possible numbers. But in any event, I'm going to write the numbers here a little lower than usual. And the reason why I'm going to write them lower than usual is because I'm going to draw a line through this. Okay? And up on top of this line, I'm going to write the front number without the square. The front term without the square. The front term without the square is just 4x. So 4x, 4x. And I'm going to attempt to treat these as fractions, 4x over 6, 4x over 6, and reduce them if possible. Now notice each of them reduced by dividing by 2 to 2x over 3. Okay? That reduces to 2x over 3. This also reduces to 2x over 3. I'll circle these. And what we're going to do is we're going to write these now as factors. So 2x over 3 would correspond to the factor 2x plus 3. This would also correspond to that factor, 2x plus 3. So we have two factors of 2x plus 3. You could alternatively, if you wanted to, write this as 2x plus 3 all squared. But I'm going to write it like this, and we'll see why in a second, just because obviously I'm going to use the ZFP. And again, you can check this. If you don't take my word for it, you can check this process indeed works. FOIL this out. I'm not going to do it here, but you can try it, and you'll get this original polynomial on the left. Good. So now, applying the zero factor property, let's see if we can apply that little bit of advice I just gave you. What do you do to find x right away? You change the sign of the number, so negative 3, and divide by any number in front of x, 2. In this case, you would get the same thing. So if you wanted to, you could write x equals negative 3 over 2, comma negative 3 over 2, but they're the same number, so I'm just going to say that this is our only number, and box that. Now, just to be technical, and we may see this in the future, since the solution technically appears twice, this is a solution of what is called multiplicity 2. Multiplicity, by the way, is just how often a solution appears as a solution, which I know is a weird thing to think about, but that's what it is. And we're going to see another method right now. All right, so here for these next few examples, I want to show off some property. Before I do that, though, I want to just relate something so we can see that it is indeed true. So in this case, if we follow the steps from before, move everything to one side so the zero's on the other, factor the non-zero side. This, if you don't realize, is a difference of squares. It can always be factored as x minus the square root of 4, and then x plus the square root of that number. Only if you have x squared minus a number, you can pull this trick off. And if you FOIL it out, you can see you'll get x squared minus 2x plus 2x, and then minus 4. The middle terms indeed cancel, and we just get x squared minus 4. So this definitely works. Applying the zero factor property, either x is equal to positive 2 from this factor or negative 2 from this factor. Altogether, we can use this new notation, plus or minus. So we can say x is equal to plus or minus 2. Okay? I'm going to erase this and show something else that we can do and just kind of jump all of this. And you can kind of always do this, and we'll be doing this with these next two examples and I think a few more as well. But here's what we're going to do. It's going to be a little more simple. All we're going to do is square root both sides of the equation. And yes, that is something you can do, but there is a technicality. And the technicality is the following. If you square root both sides of the equation, you technically get a plus or minus on one side. Honestly, what side it is doesn't matter, but normally it'll be on the non-x side of things. And on the left, the radical and x, and the radical and square cancel, so we just get x, equals plus or minus the square root of 4 is 2, and that's exactly what we got over here. It's the same thing, just a lot shorter. And this technique is helpful when you have a square already, like in these two examples, if you kind of see ahead. Now, we could try to expand this out and move everything to one side so the zero's on the other, and then factor the non-zero side, but there's an issue. And the issue is that what if it's not factorable? As it turns out, this first example will be, so if you want to try that method, by all means, pause the video right now and try to do it on your own. I'm going to do it using this new property we saw. By the way, this property is called the square root property. So let me just write it out. So the square root property says the following. It says that if x is equal to, well, I guess if x squared is equal to, there we go, sounds better. If x squared is equal to a, then that means x is equal to plus or minus the square root of a. So that's the property I'm going to be applying here. Square rooting both sides gives a plus or minus on one side. That's all it says. So in order to do this, I'm going to first isolate the square term by subtracting 1 in this case to both sides. So we get x minus 3 squared is equal to 4. Square rooting both sides leaves us with plus or minus on the left. Yes, the radical and square cancel, so we just get x minus 3 on the left. Equals plus or minus 2. Square root of 4 is 2. Adding 3 to the other side will give us x is equal to positive 3 plus or minus 2. Notice, adding 3 to both sides cancels 3 on the left and brings positive 3 onto the right, so it's positive 3 plus or minus 2. Now there are two solutions because, remember, plus or minus means plus or minus. So in the positive case, we get 3 plus 2, which is 5. In the minus case, 3 minus 2 is 1. So if you were to try this by the other method, which is expanding everything out, combining like terms, moving everything to one side to the zeros on the other, and factoring the remaining non-zero polynomial on the left, you can do that and you'll get this. You should get this. So you can try that out if you want to. Here, as it turns out, this will not be factorable if you try that method. And here's why. We're going to do the exact same thing, but I made this one a little complicated, so just bear with me. So again, we'll isolate the square first. So if you treat this as x, think of this as 3x plus 2 equals 4. So subtract 2 first. You get 3 times x minus 2 squared is equal to 2. Then divide both sides by 3. So we get x minus 2 quantity squared is equal to 2/3. Great. Now what? Well, now we're going to square root. So we're going to square root both sides. On the left, they cancel out. On the right, we get a plus or minus. So that's x minus 2 is equal to plus or minus. Here's what I'm going to do. I'm going to write the square root of 2 over 3 as the square root of 2 over the square root of 3. And this is something you can do with square roots. Square root of a fraction is the fraction of the square roots. You can split it up over fractions. Okay. The next thing I'm going to do, obviously, is add 2 to the other side. But I'm going to do something else when it comes to this fraction involving the radicals, and that is I'm going to do what is called rationalizing. I'm going to multiply top and bottom by the radical so that the denominator will have no radicals. Notice, radical 3 times radical 3 is radical 9, and that's 3. Square root of 9 is 3. So on the denominator, we'll get 3. In the numerator, we get the square root of 2 times 3, which is 6. And moreover, I'm going to write 2 as 2 over 1. Let me redo that. And the benefit of doing this is so we can combine into one fraction by multiplying top and bottom of this by 3. And we'll end up with 6 plus or minus the square root of 6 all divided by 3. And that's the answer. Now, of course, there are two answers here, and you can split it up as the positive case, comma, the negative case. The only problem, though, is you can't combine like we did here because of that square root. And the reason why this tells me that it's not factorable is because if it was factorable, you wouldn't get any square roots involved. So this is a scenario where you can actually solve for x when the polynomial isn't factorable. The only problem is that the equation has to be of this form. It has to have that square. But there's a way we can actually always make it like that, and we'll see that right now. Okay, so now this next method allows us to convert any equation, any quadratic equation, into that case where we have a square, and we can just isolate the square and apply the square root property, and it's called completing the square. And it says if x plus b over 2 all squared, well, if you have that, x plus b over 2 all squared, it's equal to x squared plus bx plus b over 2 all squared, like this. And there's a nice visualization, but if you FOIL this out, you'll actually get this. So it's not super surprising of a fact, it's just a kind of weird formatting of a fact we kind of already know. But here's a nice visualization of it. If we have a square, x by x, so x squared, and let's say it's multiplied by bx, so these two. Okay, that's usually what's going to be given, and we'll see that in a second. If you half the middle one, you'll have b over 2 times x. So these two rectangles here are b over 2 times x dimensions. So if you were to put all these together and get that shape, the shape you get almost wants to be a square. And what it would be missing is this little red square that I've drawn here in red, obviously. And it's a b over 2 by b over 2, so its area would be b over 2 all squared. So really what I'm doing here is I'm looking at the areas of these pieces. The area of this is x squared. The area of this is b over 2x. B over 2x. Notice they combine to just bx. So these two basically. So these three circles are those. And the one in red is b over 2 all squared. Okay? So this is the visualization of why it's called completing the square, because you rewrite it as one whole square. And notice each of these side lengths now is x plus b over 2. So it's a square of dimensions x plus b over 2 by x plus b over 2. Something to think about, but that's a nice visualization of that fact. So now let's take a look at these few examples I've written out here for us. And the first one is x squared plus 6x plus blank is equal to x plus something squared. So we're going to complete the square. And to do that, we're going to apply this. We need to half the middle number and then square it. So what's half of 3? I ruined it already, didn't I? I meant to say half of 6. What's half of 6? Squared. Half of 6 is 3, and then squared would be 9. Okay? And here, what would go here is just the half part before squaring. In other words, just 3. If we take a look at this and try to apply this, if you're given these two, x squared and bx, it would complete as x plus half of b all squared. So you can half 6 to get 3, and then square it to get this number. So let's see if we can follow that pattern. So if you half 4, you get 2, and then if you square it, you get 4. So these statements that I've completed here are actually true statements. If you FOIL these squares out, you'll get these two. So if you write x plus 3 times x plus 3, FOIL it out, you'll get this. Similarly for x plus 2 times x plus 2. Here, it's a little different because the middle sign is negative. So when the middle sign is negative, then this middle sign will also be negative. So it's no coincidence that these are the same. These signs will always be the same. Notice these are both pluses in the above two cases. That'll always be the case. So same pattern though. Half the middle one, we get 5. And notice half of negative 10 technically is negative 5, so the sign carries over. Squaring that is 25. Okay? These are just quick examples of completing the square. And now I'm going to solve x in this equation using these facts. So, first off, notice this polynomial actually is not factorable. So you can't even factor this. You can't even solve this by factoring, actually. But what we can do is we can forget about 1 for a second, throw 1 off to the other side to just focus on x squared plus 8x. And we're going to add some special number to both sides so we can complete the square. So we're going to add something to both sides. Okay? Now, we want to write the left side as a square. Notice since the middle sign is positive, let me highlight that in red, then the middle sign here will also be positive. Okay? It looks too much like a plus or minus, but you get the idea. The signs are the same. Now remember, to complete the square, you half the number, and that'll be inside of the square here. So half of 8 is 4. And then squaring 4 will be 16. So we need to add 16 to both sides of the equation to balance the equation. So in doing that, what are we left with? Well, we're left with a 17 here. Okay? So now what? Well, now I guess all we need to do is square root both sides. Remember, when you square root things on the left, the square and square root cancel, so you just get x plus 4. Here you get a plus or minus, the square root of 17 in this case. And then subtract 4 to both sides finally. We get our solution, x is equal to negative 4 plus or minus the square root of 17. And that's all I'm going to do for completing the square. We're not going to really see it too much, but it's a really nice technique that we can use. Instead, I'm going to move on to the last technique we'll see for this section, and that'll end the section. All right, so now we're going to move on to the next technique I wanted to talk about, the last technique for this section anyways, and it is called the quadratic formula. Before I get into it, though, I want to say that I made a slight mistake earlier. For some reason, I wrote 17. I was adding the numbers. I didn't do it correctly for whatever reason. I kind of paused for a moment because I recognized that it should have been 15, but I just wanted to carry on and not even think about it. But anyways, yes, it is 15. It doesn't really affect the answer too much. That 17 I wrote earlier should just be a 15, basically. Anyways, we're going to actually attempt to do it again using a different method, so we'll see that right now. But first, let me talk a little bit about this quadratic formula. So the quadratic formula says if ax squared plus bx plus c is equal to 0, so any quadratic equation as long as 0 is isolated, you can solve for x using this. X is equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. A lot of people remember this. You won't need to remember it. You can, well, it'll be given during any exam, just knowing how to use it. So let's actually try to see it in use right now, shall we? So first off, we need to figure out what a, b, and c are. Now, a common mistake is to include x in the equation. Don't do that. The values of a, b, and c are the numbers in front of the x's. There's no x's included. Here, what number is in front of x squared? It's 1, technically. The number in front of x is 8, and then the constant term is 1. So these are our values of a, b, and c in that specific order only. In other words, what is a? It's 1. What is b? It's 8. And what is c? It's 1. Okay, great. So notice we did this example earlier, different method, but we got something. Let's see what quadratic formula yields. It should yield the same answer, but it'll be a little different. Well, the answer is the same, but it'll the process is obviously more different. So we're going to get x is equal to negative b, I'm just following this, so negative 8, plus or minus the square root of b squared, that's 8 squared, minus 4 times a, which is 1, times c, which is also 1. All divided by 2 times a. Okay, great. But now, on top we have negative 8 plus or minus the square root of, let's see, inside of the square root we have 8 squared, which is 64. And then negative 4 times 1 is just negative 4, so that's minus 4, all divided by 2. Perfect. So now what are we left with? We're left with negative 8 plus or minus the square root of 60. 64 minus 4 is 60, all divided by 2. And no, it doesn't look the same, but they are the same because we can actually simplify this radical. So what do I mean by that? Well, as it turns out, the square root of 60, you can write 60 as 4 times 15. Why 4 times 15, you ask? Because if you split this up as the square root of 4 times the square root of 15, the square root of 15 can't be broken, but the square root of 4 can. What's the square root of 4? It's just 2. So this is 2 radical 15, actually. So replacing this radical with 2 radical 15, we get x is equal to what? Well, negative 8 plus or minus 2 radical 15, all divided by 2. If you factor 2 from the top, by dividing each of the terms on top by 2, negative 8 divided by 2 is negative 4. 2 radical 15 divided by 2 loses the 2. And then canceling the 2's out finally gives us the exact same answer that we got earlier. Let me just write it. Negative 4 plus or minus radical 15. So you may or may not like this. A lot of people honestly like this, even though it involves a lot more arithmetic and possibly simplification of radicals. It's less wonky, I guess you can say, than completing the square. Completing the square takes a little bit of time. People generally don't like it. So it's okay if you don't use it at all. I at least wanted to talk about it still. And I've basically justified everything we've been doing today except for quadratic formula. I would love to show you the proof of it. It just takes too long and is a little involved. I just showed it on the first day of class though, so there's that if you attended that. But let me just say this. To prove this formula, it's not that bad, honestly. You would just have to complete the square with letters. So it's kind of bad. I kind of lied here. But anyways, we're done with 1.4. Now we're going to move on to 1.5 in the next video, and I will see you then.